Yeah, no, it had to be
Nice.
except being recorded. So, welcome everyone. It's a privilege for me to welcome back RichardMurray from Caltech. He's well known to this university and department. He's actually an honorary doctor of the university, and he has been at California Institute of Technology for quite a long time, after finishing PhD at Berkeley. He has been a co-founder of control and dynamical systems as an option at Caltech. He has been division chair for engineering and applied sciences for some years, but now he's heading another division of Caltech, namely bioengineering. So we are very happy to have you back, and we look forward to your presentation.
Great, thanks. So it's great to be back in Lund after obviously the COVID delays and other things. I think the last time I gave a talk here was maybe 4 years ago. And so, and I'll remind you what that talk was about, because I'll build on some of that. But I'll also say, so like every 5 years or so, I decide to kind of revamp the talk that I'm giving, that, you know, the new stuff in. So this is the first time I'm ever giving this particular talk. So if it's a little bit rough, I apologize ahead of time. And then, you know, you sort of figure out what works and what doesn't. Like they were supposed to laugh at that joke, but they didn't. So I have to change that one, right? Things like that. So this is my first run through this particular combination of things, right? I mean, obviously the material. Okay, so so I'm interested in, been interested in for a while, these safety critical systems and safety critical autonomous systems. So saying self-driving cars, you know, UAVs, right? Sort of things of that sort. But the part that's sort of newish is on the top line, which is this operational test and evaluation. So I hope by the end of this, right, you'll understand that they're interesting control-oriented problems, right, in thinking about operational test and evaluation, and, you know, what the heck all of that means, and that these are important things for us to solve, you know, both, you know, as engineers generally, as control engineers more specifically, as society, right? I mean, these are all right. So, you know, what are kind of safety critical systems, right? You know, the obvious one, and the one that I have a lot of background in, is, you know, aircraft, right? So, you know, we all get on an aircraft every day, not every day, you know, every month, maybe some of us, and we really trust these systems, right? So, you know, you pretty much think you're going to get to where you're going, right, and not have to worry about it, and it's going to be safe. And that's because the engineering discipline has developed, you know, many ways of designing these ultra reliable systems, and aircraft are really amazingly reliable, as I'll sort of tell you a little bit. There's a new technology that's coming, of course, which is self-driving cars. This is one from Nutonomy. I use Nutonomy because some of my early students went to work at Nutonomy. And, you know, self-driving cars are also a safety critical system, right? Because they're running around on the streets around us, right? So if you go to San Francisco, you walk around for 30 minutes, I guarantee you, you will see at least a half a dozen self-driving cars. I mean, they are really quite a few of them wandering around in the city and other things. Waymo has a garage that I have an apartment there, and they have a garage that has 500 self-driving cars, right, sort of sitting inside of it, that they take out, and they're driving around all the time in the city of San Francisco. And they're just one of, you know, several companies that are testing in San Francisco. So Waymo, Cruise, Zoox, right, they're all testing cars out. So you see these driving around, they have safety drivers in them right now, right, because they don't trust the systems. But these are, you know, eventually, if they're going to be truly autonomous, and I'll use this as the example going through these self-driving cars, we have to figure out how to make them safe, and we got to figure out what's safe enough and how to. There are lots of other safety critical systems. The power grid, essentially, and this is, you know, a picture from the book with Carl, you know, it's another safety critical system, right? Because, you know, it's powering all of the things that are going on, and we need to make sure it has to have super high reliability, right? And so how do we think about the design of these systems? And again, I think engineers on the left and right, we've succeeded in doing this. You know, I'm not anticipating the power is going to go out while I'm giving my talk, right? You know, and probably won't go out the entire time I'm in Sweden, right? And so, you know, that's, you know, it's pretty reliable, right? So how do we do that? And then how do we take some of those lessons? So just to kind of, you know, indicate a little about, you know, kind of what some of the challenges might be. So if you look right now at human-driven cars in the United States, the number of deaths per mile driven is about 7 deaths per billion miles driven, right, in the US. Right? So for every billion miles of vehicle traffic that goes on, about 7 people die. Traffic accidents, right? Somebody runs into you and they run into you at a high enough speed that you die. And so you can say, well, society clearly tolerates this level, right? You know, we all buy cars, we get in them, we understand they're dangerous, but we're careful, right? You know, we have safety belts and airbags and all of these things that help bring these numbers down, right? You know, over time they've been coming down. He's trying to get it way up in the front. So we could say, well, this is maybe good enough, right? And I think one of the interesting questions is what's good enough? And then when we understand what's good enough, because, well, how do we know, right, that if I release a new technology like self-driving cars, right, how do I know that they're that safe without driving them billions of miles and finding out the hard way that it's 100 times worse, right? That would not be good. And just to give you some sense about, you know, why this would be a challenge, if you had 7 deaths for every billion miles, it turns out that in the United States, that works out to about 35,000 people per year are killed by traffic accidents, right? So 35,000 people per year. 35,000 people per year. If 1% of the cars in the US were self-driving cars, and the penetration of electric cars, just to give you some sense, is already above the 1% level in the United States. All right, if 1% of the cars were self-driving cars and they were as safe as human-driven cars, right, that would be 350 deaths per year, which basically means every day somebody in the United States would be killed by a self-driving car. So every day in the New York Times or the LA Times or the Washington Post, right? Professor in Pasadena gets killed by self-driving car, right? You know, professor in, and maybe they're all professors, right? You know, sort of, you know, doctor in wherever gets killed, small child gets killed. Probably the industry would not survive, right? At a level of every day being told that this dangerous technology is killing people, right? Every day, even though it's as safe as humans. So it's not clear that, right, 7 deaths per billion miles is enough. Right? And that's a pretty hard number to hit, right? All right, so, you know, another place you can look is the aircraft industry, right? So what are the statistics there? So the statistics there are 0.07 deaths per every billion miles flown. So it is 100 times safer to fly from here to Stockholm than to drive from here to Stockholm, right? Or these are California numbers on the right-hand side. So to get to San Francisco, you should fly, not drive, right? At least if you're worried about dying, right? Because it's 100 times safer to do that. And so I think one interesting question is, and you could believe that at 100 times safer, right, it would basically be 3 deaths by self-driving cars per year. That society would probably tolerate, right? Not very often would you read about, you know, sort of a self-driving car killed somebody, and the industry would argue, but look how much safer we are than humans, right? Because 35,000 people a year are dying from, you know, sort of humans driving around, right? But cars are 100, or self-driving cars are 100 times safer. So certainly if you could get there, that would probably be enough. And I think the question is, could we get there, right? Could we bring 7 deaths, right, per billion miles for human-driven cars down to 0.07 for self-driving cars? And of course, one way to do that is to think about maybe taking some of the lessons about how we do it from here, and I'll tell you a little bit about that, and bringing them back and saying, do they apply, right? Can we take the lessons here? So that's one of the things I'll talk about. Okay, so what I want to do is, you know, I'll motivate this a little bit more. I'll give you a little bit more detail about all of this in the context of autonomous vehicles. I'll talk about some of the tools that we're using to sort of think about this problem, in particular from linear temporal logic and computer science and formal methods. That's the review part, in the sense that that's what I talked about when I was here last time, because we continue to work in that area. And then I want to tell you about the new stuff we're doing, which is on operational test and evaluation, OT&E, and sort of how to think about that, right? And operational test and evaluation is actually doing testing on real life situations, right? You know, sort of aircraft go through operational test and evaluations, or flight test phase, right, where you go through and you test the limits and you make sure it all works. And so I'll tell you a little bit about that, and I'll end just with one slide and say, okay, well, you know, what are the okay? So let me just give a little bit more detail about sort of these classes of systems and what's going on. Okay, so if you look at self-driving cars, right? So here's a bunch of different self-driving cars. This is Waymo, this is Autonomy, this is actually Waymo again, Google. They got rid of this. This was an interesting car because it had no steering wheel in it. This is a company called Zoox, and so they're in San Francisco area. And this is intended to be doing transport, people transport, right? So it's optimized for letting you get in and out and other things. No safety driver, right? So, you know, these cars are in testing right now, and they have a driver who's sitting there, you know, ready to take control. You know, if you're testing something like this, there is no location. There's not actually a windshield. The fronts and the backs are actually opaque. You can't see through them. And so different thing. This is maybe also a self-driving car. This is a Tesla, right? And so the autopilot system on a Tesla, right, you know, is sometimes billed, right, you know, sort of full autonomy, maybe. So the SAE, Society for Automotive Engineering, established this set of kind of automation levels that they use, SAE level. that range from no automation, which in fact, there's no cars that do this anymore, to full automation. And the idea is there's no automation, there's driver assistance. So this would be things like the things that beep if you start to change lanes without signaling and sort of things of that sort. So they're just kind of alerting systems. To partial automation, so some automated functions. So for example, self-braking systems, if they see something in front of you, they'll automatically brake, sort of things of that sort. To conditional automation, so in conditional automation, right, the driver is, this would be something like cruise control with lane keeping, right? And it will let you know if it can't take over, right? So maybe Tesla is sort of at this level right now. To high automation, so the vehicle is capable of performing all of the driving functions, not just sort of staying in the lane and keeping distance, but taking an exit ramp and coming up to an intersection and doing something. But the driver may have to control the vehicle and it can't handle everything. So it might say, I can't do this, you're too crowded of a city, you have to drive. To what they call full automation. So now the system is capable of doing everything, right? The driver might intercede, but is not required to. Basically, it will always operate safely. So these are the levels they define. I think that these first three levels were there already, right? We do this, it's safe, right? We have, if you buy a new car, right, it probably has many things in it that will automatically correct for you, right? If you're on icy roads, the anti-lock brakes were one of the early ones of this, right? There's been very, conditional automation, I think is a question. And to me, you probably can't read it, but the challenge is down here. So the driver must be ready to take control of the vehicle at all times with notice. Basically, in this version, this conditional automation, it's like you're driving down the road, right? And you're on a highway and, the automated system is doing its thing. And then all it says, this is too complicated for me, you take over, right? That doesn't seem like a great idea, right? Because what were you doing while it was doing everything? You were reading the paper, you were texting, you were whatever, right? And then all of a sudden you hear this ding, 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 right? Your turn, right? And you look at it, right? And you haven't been paying attention, right? You haven't been doing it. So in fact, I actually think this is probably impossible, right? Cannot be done. The reason is just this handoff is a very bad idea, right? Because the whole point is, right? And we're people, right? So, and this is the problem with Tesla, by the way, right? These Tesla cars, people are dying. And the reason is because people, you're supposed to have your hands on the wheel, et cetera, but people are like putting one hand on the wheel and then they're checking over here, et cetera. And then the system essentially, right, sort of does something and you don't have time to recover because you haven't been paying attention. So I actually think this is a bad idea, right, that we shouldn't do. Now, this one, right, high automation, right, it can do, the vehicle can perform almost all driving functions, right? It's performing them under certain conditions. So I can say, look, it's an open road, it's clear outside, there's no ice, right, I'll sort of drive. And then the way they've said it is the driver may have the option to control the vehicle. I'll tell you that for these companies, right, they are not planning to have self-driving cars be something that you buy as an individual, right? This is not the plan. They're planning on offering ride services, basically Uber, right? And so they're going to do something where now who's the driver, right? Because, right, they don't want to put a driver in there. If you have a driver in there, that's just normal Uber, right? They're not saving any money, right? And so instead of thinking about it as the driver, they mostly are thinking about teleoperation in some way, right? So there's somebody connected across the 5G link who come in and see all of the views and everything else, right? And might be able to take over some limited functions. Obviously, they're not going to dynamically drive the car. The latencies are probably too big, right? So the way to think about high automation, right, is that the car would be able to say, there's something too complicated going on. I'm going to contact teleops. I'm going to pull over and slow down and bring the vehicle to a stop or to a safe condition or something like that, right? And so I think there's a question about, can we as engineers develop that technology? Right? So I don't know yet, right? And can we get it to be safe enough to do that? And then this last one, the way it's written, right, has this statement at the top, and the statement at the top says that the vehicle is capable of performing all driving functions under all conditions. I don't think so, right? I mean, it's just not going to happen, right? In my opinion. Now, you could do it, right? If I had a $10 million car, right, I could probably make it, have all the sensors and everything else I need to do that. But at $10 million, right, first off, none of us are going to buy one. Second off, I don't think a car company can, a mobility company, right, can sell enough, you can't use it for long enough to make back your money, right? If every vehicle is costing you $10 million, right? Compared to now, it might cost you, $50,000 for a nice car, right? No big deal, right? So this is going to be, sort of 200 times as expensive, right? So you're going to pay 200 times as much for Uber? I don't think so, right? Okay, so I think this one's actually not viable either. So I want to kind of focus today on this one, right? So just, can we build high automation, right, where the vehicle is performing under certain conditions, things, and how do we know that it can do it? And it can bring you to a safe condition, right? If it needs to. So that's kind of what I want to focus on, that class. All right, so as I mentioned, sort of aerospace does this, and this question about how safe do cars need to be, right? So currently we get 7 deaths per billion miles. Another transportation mode is trains, right? So I took the train down, right, from Linköping, from Norrköping actually yesterday. And so trains turn out to be about 20 times as safe, right? On order, so 0.1 to 0.4 deaths for every billion miles traveled. And is miles the right metric, et cetera? It's a good metric, right? Just because it's we're trying to get from one place to another. Miles is a good metric. So buses and trains about 0.1 to 0.4, and as I already mentioned, right, 0.07 deaths per billion miles, right? So another factor of sort of 5 that we get from air travel, which is pretty amazing actually, because if you think about it, right, aircraft, if something goes wrong, right, you're 30,000 feet in the air, right? This is not a good place, right, to have a failure. And so, but again, as engineers, we've sort of done this. So how have we done this? Well, there's really very strong certification processes that are involved. So there's something called DO-178C. It's an example of for flight control software. It is the certification standard that you have to meet. And they categorize things as hazard classes. So something that's considered to be catastrophic if a failure of that function would lead to loss of multiple deaths on a plane, right? So the 737 MAX, right, was a class A failure, right? Because when that augmentation system went out, right, people died. So that's a class A failure. And the certification standard says that you can have no more than one failure of such systems every billion hours of flying. So now that we changed the unit to hours. A billion hours is 100,000 years. Right? So that means, right, this is software. Your software, right, has to be able to run with hardware failures, software failures, computer failures, et cetera, for 100,000 years mean time between failure. That's pretty high, right? How do you do that? Well, you don't have just one piece of software, right? You've got multiple computers, you've got multiple sensors, you've got multiple everything else. When you land, you check and make sure it's all good, right? You do a lot of things to make sure that it works. But that's the way they categorize it. And then there's this standard, right, that says how do you, basically certify at that level, right? How do you, as an engineer, come and say, yes, this thing will fail less than 100, once every 100,000 years or once every billion flight hours. By the way, if you look at deaths in the world due to air traffic, right? We just had a couple of years ago, right, from the 737 MAX, they pretty much hit this level, right? So if you look at the number of people who died, but you look at how many miles were flown or how many hours were flown, right? We're basically at that level, right? So this actually works. People die at a level of 0.07 deaths, and that works out to that many flight hours, and we're actually there, right? So we know how to do this as engineers. The engineering community knows how to do this. All right, so how do you do that? Well, one thing you do is just fault tree analysis, right? So if you look at DO-178C, one of the things they can say is, look, you've got some subsystem. This subsystem needs to function in order for this to keep going. I need to have a failure rate on that function. And so I say, okay, I've got to have a, say, 10 to the minus 8 on that one because I've got another subsystem that's duplicated or something like that. And then we'll say, okay, well, this could fail because any one of 3 things could fail, right? And so we'll basically do an or type of an operation. If this fails or this fails or this fails, it leads to this. And so we impose a factor of 10, typically at each level we go down. So this needs to fail, right, no more often than every 10 to the minus 9, right? And then we might do an and operation on this one. So this one, right, if I have 10 to the minus 9 here, let's say engines, right, say, look, I need 100,000 or 10 to the 9th flight hours of the engine running, right? Okay, well, how do I do that? Well, you put more than one engine, right? And so you might, or electrical power would be another one, right? You say, look, I need my electrical power to be up in order for my computers to run. So that left engine can provide enough electrical power to keep the plane running. That fails every 1,000 hours. The right engine, right, can be running and keep the plane running. That fails every 1,000 hours. The APU, the auxiliary power unit, can power up all of the critical systems. That fails every 1,000 hours. If I can make sure they're all independent, right, then the likelihood, right, that one of those is not available, right, that's only need one, right, is going to be the product of those things, right? So I get 10 to the minus. So that's the way you do it. So now 100,000 hours, okay, that I can do, right? 1,000 hours is not that long. And by the way, these planes land and we check them and we do other things, right? So that's the way that we get these center reliability. And so these fault trees allow us to do that. And so you just do all of that analysis, just statistics, and you can make sure that you kind of get to the right spot. All right, so that's one way that you do it, is just to do these fault tree analysis. Another one you do certainly is a lot of model-based design, right? So you're going to do simulations, you're going to do hardware in the loop, software in the loop, you're going to test the hell out of these things, right? And you're going to make sure, where do the numbers come from that say these engines fail, right, every 1,000 hours. You're going to run it for 1,000 hours or 10,000 hours and see how many they fail. You're going to run 10 of them, right? You're going to do those things. Obviously, if it's a component that's already in flight, you have statistics on its failure rate, right? So probably very few of us have been on a plane where an engine failed. I can guarantee you all of us have been on planes where sensors fail. The sensors fail all the time. You don't even notice it because they're redundant. They basically, you're allowed to fly with sensors failing because they fail so often that if you couldn't fly with sensors failing, we'd never get on the plane. Right? I mean, because they'd be ground. All right, so we do lots of model-based design and simulate things, right? And we compare those simulations, et cetera. We do a lot of fleet-wide analysis. One of the things about both self-driving cars, but also airplanes is the rare cases matter, right? What drives things at the 10 to the -9 is that you just happen to have a situation where the engine failed as you were landing and there was a crosswind, right? Those are the things that matter. So you have to think about, but how often is that going to happen? Very rarely. But if I'm flying thousands of planes every day for thousands of miles, someplace in the world, that's going to happen reasonably often, right? And so that's kind of what drives these things. All right, so there are these ways to do it, because obviously you've got certification requirements. You have to then decide, how do I actually make it work? And so we use a lot of redundant and fault-tolerant hardware, right? So you use computers that have automatic other computers, right? Nothing is single string in the sense that one failure would cause the fail. In fact, by the way, the 737 MAX, why did that happen, or part of why that happened, it's a complicated story. But one of the things that happened was, so it was MCAS, the maneuverability augmentation system, maneuverable characteristic augmentation system was what MCAS stood for. When it was originally designed, it was intended to make it a smoother flight and help the pilot out a little bit. And it was categorized as the next level down, level B software. Its failure would not lead to death on the plane. It might lead to major damage on the plane, right? You could damage the landing gear or other things. What happened was, in the engineering process, they started to have some problems in the operating envelope. And essentially, right, it became a hazard class A, category A flight function. But they didn't classify it that way. In category A, you never allow a single sensor failure, a single failure of any type, to stop the function. That's just a written rule, right? No single point of failure. But in level B, you do. And they were using level B processes for a level A function. And that's part of what went wrong in that. All right, so, but you typically would not allow that. So you have redundancy, you have monitors. They'll do things where they will run previous calculations through a CPU and make sure that the answers still match, right? Because you might have gotten a bit failure on your memory someplace in your CPU cache. So you want to make sure that doesn't happen. So you're like running calculations through just to make sure that your CPU is still giving you the right answer. And that's the type of things you do, right, to make sure that these things are still running, because latent failures are tricky. All right. The other thing about aircraft is very structured operating environments. You got airspace, air traffic controller, you're being told to do this, that, or the other, right? So, it's not traffic, right, where all sorts of things are going on. Well-trained personnel, right? So, pilots have to go through training. Again, this was part of the 737 MAX, right? So in principle, it would have all been okay, but the pilots didn't quite know what to do, right? Because they hadn't been trained on what happens if that sensor fails in this mode, blah, 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 right? Flight attendants, right, know how to get you out of the plane in the right amount of time, right? Safely, all of those things, that leads to fewer deaths. And then, finally, I think, a characteristic of this in the aerospace industry is, these are very expensive. It's about $1 million per passenger, right, to build an aircraft, right? Because these are 250, 300, passenger aircraft. And, if you had to buy a car, 4-passenger car for $4 million, right, you could make it pretty safe too, right? Because you could put a lot of redundancy in hardware and other things. And again, just come back to this point that, that's not going to work economically, right? Self-driving cars are not going to do that. So I think that there are areas where we can certainly, and companies are, there's a lot of relevance to what we're doing here in aerospace that can be carried over, right, to the self-driving cars. So I think we can apply these techniques. These things on the bottom are really very different, right? It doesn't apply. You don't have structured operating lines. Big sky, there are air corridors, there's all sorts of sensors along that tell you where you are down to precision. You're driving in Lund, right? And people are cutting across the street and bicycles and other things, right? Because in Norrköping, you may know that in Norrköping, there's this great intersection that has no rules, right? It says you're coming up on this uncontrolled intersection, it's a big circle. There's 5 roads that are coming in from different directions. No lights, no stop signs, no nothing. People are just crossing all over the place, right? Bicycles, and it works, right? Somehow, right? But it's not very structured, right? So it's not something you can say, no, there's a light and you can't cross the light until it says it's okay. And I can do none of that. But self-driving cars might drive in Norrköping one day, right? And maybe the city council will decide to change it and put stoplights there, right? But maybe not. Right? Okay, so so that's a little bit about aerospace. All right, so now how do we want to approach this? All right, so we need a rigorous, right, a way to approach these problems that we really understand. And so we've obviously been using formal methods and other things, and there's some advantages, and we want to try and exploit the structure that formal methods use. Okay, so hopefully for most of the people in the room, this is a kind of familiar diagram, right? It's their standard control diagram. You've got some process or plant, right? You've got some disturbances, you've got some output, you've got some weighting functions, you have some unmodeled dynamics, you have disturbances that are coming in, you've got some controller. You're trying to design this controller such that essentially the norm between the disturbances and the output, right, is got some norm gamma for all unmodeled dynamics, right, that are bounded in some appropriate way, right, with all of the, whatever symbols need to be on the bottom to put them in the right classes of it. All right, so we're interested in doing things that are very similar to that, but now at a different level. In a self-driving car, the problem of keeping the lane and holding the speed is not the fundamental problem, right? The fundamental problem is, there's somebody in front of me and somebody starts to come out. Do I veer over to the left lane or do I stop, right? It's a little bit more discrete decision-making. I start going into an intersection. Is it my turn to go? Can I go? I start going, somebody else goes. Do I stop? Do I turn right? What do I do, right? So it's this discrete level. But in fact, to some extent, and I should say, this is a slide, I used exactly this slide, right? Sort of 4 years ago, right? In this, probably not this room, over in M building, right? The equivalent room. And this was at the end of the talk, right? And I sort of said, okay, well, if you now ask the question, well, what does this look like for the discrete decision-making? It's really the same in some sense, right? You have some discrete decision-making process. I can turn left, I can stop, I can signal, I can do all of these things, but they're discrete, right? I do this or that, right? And then, the environment, right, does something. People in front of me stop, go left, change lane, stop in front of me, do whatever they're doing. And I interact with that, right? Sort of, I do something, they do something, right? And we sort of go back in this kind of feedback interaction at this discrete level. We can have discrete external things happening, that the lights change. The lights, let's say, are on a fixed schedule. They may not change because I'm entering the intersection. Some do, some don't, right? But I can have discrete things that occur. A flat tire happens, right? I just think of that as a discrete event. I suddenly lose that. And then we need a controller, and this controller now is a discrete decision-making system, right? My left tire just went flat. Should I pull to the side of the road or should I stop in the current line? Right? And then, of course, there's lower level stuff also that's going on. Okay, now I have to actually stop with a flat tire, right? That looks more like this. And it's the interaction between these two. But it turns out that this class of systems has a very similar structure. So here I've written down a specification for the controller, right? I'd like to design a controller. What might the specification for the controller here be, right? I need a mathematical language to do that. And so we use a language called linear temporal logic or signal temporal logic. This is what a formula looks like in that mathematical language. And for those of you who've seen me talk before, you may remember what some of these symbols mean. I will tell you again in this talk so that you don't forget. This is a particular class of problems like H infinity, and nobody outside of our field knows what the hell H infinity means. This is called GR1, and nobody outside of computer science knows what GR1 is. But this is a class of specifications, right? Just like this is the class of sort of control specification. And roughly speaking, this has these components that are the same. Really what you have is you have some description environment. What's the size of the unmodeled dynamics? How big are the disturbances? Right? And then you want some system specification. Keep the overshoot, right? But smaller in some amount, the deviation, whatever it happens to be. And in the context of these sort of standard control systems, the environmental spec is the disturbances in the unmodeled dynamics, and then the system spec is some gain specification. But it turns out that in these GR1 synthesis, it's the same. You have some safety and liveness specification on the environment. The intersection will always eventually be clear. Cars will not run into me. Right? I have to assume that. And under that assumption on the external part of things, then I want to make sure that I don't run into people and I always get to where I'm trying to go. Right? And so it has this same flavor of you've got to have some assumptions about the environment, some description of what the environment is. But now this description is a behavioral description, right? Cars can turn left, stop, go, get behind me, get in front of me, right, at that level. And then I need to be able to, right, sort of make a similar behavioral kind of event description. All right, and so as already said, in the context of systems that we care about, so this is a self-driving car that we built, but put one of the other ones, more modern ones there, both come into play, right? Because of course, this higher level decision-making is sitting on top of, right, the lower level. And so this was the slide that I used at the very end. So I ended my talk last time, 4 years ago, 4 years and some number of days, with this slide. Okay, it's exactly this slide. Because I copied it from the presentation. And so what I said at the time was, the systems are too complex to be tested by trial and error. Systems are too safety critical to be tested by trial and error. What were we doing? We were doing at the time to specify and synthesize. So like in control systems, you don't really make a controller and then go tech this, right? You basically say, this is what I want the controller to do H infinity synthesis and synthesize a controller that satisfies the specs. At that time, and still, we were saying, well, this is a specification, here's a system description, synthesize the controller, right, in order to do that. And I'll remind you a little about what that's about. One of the other things I said was you don't want to just lump it all together and say it's one big complex hybrid system. You want to maintain the layers and keep track of that. Again, I'll mention. And at the very end, I said, contract and test synthesis, right? Because that was sort of what we were just starting to do. And this talk is really about, okay, test synthesis. So that's what I'm going to tell you about today. Okay, so this kind of, puts us in the context of things from proof. All right, so I'm just going to quickly remind you of some of the things that I told you last time in terms of the math, so you at least follow some of what we're trying to do. So the first thing is you can think of this as I've got a continuous system, I've got a continuous cost function, right? But I also have a discrete part. Here I've written it as a guarded command language. Just think of this as a finite state machine that describes I can turn left, I can turn right, other types of things. And then we've got some sort of specifications. Never run into people, always make it your goal. And we can write down the sort of description of this in this layered way. And again, this is a slide from 4 years ago, where we have the continuous process. We have some inner loop type controller, right, lower level, keep me on my trajectory within some amount of distance at the right speeds, et cetera. We have some trajectory generation level. I want to change lanes. I need to avoid other cars, right, sort of things of that sort. And then we have this discrete decision-making layer, right? Is it my turn to go, your turn to go? Do I stop? Do I turn left, right, go? And I think that we should maintain the separation of layers, solve problems at the different layers, validate solutions at those layers, and then make sure that when we connect them together, it sort of all still works. And so, I'm going to focus today primarily on this top layer, but its connection to the next layer down matters. All right, so just briefly to remind you what these funny symbols mean if you've not used them before, and I'm working on getting every controls text. So this is in the book that Carl and I wrote in chapter 15, which is not in the printed version, but not in the current printed version, but it's there. A little bit about what these symbols. So just in linear temporal logic, we talk about sequences of events that occur, like discrete event systems, right? And the symbols that we use are something might eventually occur. That is, at some point in the future, the following statement will be true. Something might always occur. That is, at all points, right, from now into the future, this property is true. And we can say that something has to happen at the next time that the state changes, right? So something's not true now, but it'll be true at the next. And we can use these to reason about and describe behavior. So for example, if something's eventually true, some property A, maybe A is not true, but at some point A becomes true. And then after that, I don't care, right? The property, so if I had a sequence of decisions that happened, et cetera, and I look at properties of the state, discrete properties of the state, am I in the right lane? Have I stopped? Other things? Then eventually this is true. If at some point in the sequence, it becomes true. And then after that, I don't care. Always means it needs to be true at every state. I'm always at least 1 meter away from the nearest car to me, right? That might be something. There are other operators that you can do, and you can combine these. So for example, we can say, if something is true, that implies that something eventually is true. Like if the light turns green, eventually I go through the intersection. We can do things like always eventually. It's always eventually the case that I will get back into the proper lane, right? So I may get out of the lane, but I'll come back in. I may get out of it again, but I'll come back in, right? I'll always eventually be, in the proper lane. I'll always eventually check my rearview mirror, right? I'll always eventually. We can do eventually, always. Eventually, I will bring the vehicle to a stop, and I will stay stopped, right? And you can combine these, right? Maybe if some property occurs, I have a failure, then eventually I will bring it to a stop and stay stopped. It would be a way to describe that discrete behavior and various other things. And so we can combine all of these things. There's another version of this called signal temporal logic, where we take into account that not everything is discrete. One is just to recognize that you can have continuous variables. And you might say, I need to be within 10 meters or something. This is kind of a trivial one. More important are things where you say something might not be true forever, but maybe it's true in some time period. Between T1 and T2, this should be true. Or something occurs and within a certain amount of time, then something else will be true, right? I respond quickly enough. So we know how to say all of those things. And so we can write simple descriptions and specifications. So if you have in Europe, a light might follow this finite state machine, right? It's green, and then it turns yellow, right? And then it turns red. And then based on somebody, coming up to the other direction or whatever, it goes red, yellow, so it tells you I'm about to turn green, and it turns green. And you say, well, what are the properties that I want this to satisfy, right? What are the specifications for a properly functioning traffic light? That's a system description, maybe or maybe not. It satisfies these properties. Here are some, right? You can say, look, I'd like that a traffic light always eventually turn green in any given direction. Probably a good property. I'd like that it's always the case that if the light is green, that it does not turn red at the next step. Because I don't want it to just go from green to red because there's no warning. Right? A more complicated one might be, it's always the case that if the light is red, it will eventually turn green, and it will not turn green until yellow. It's turned yellow. Right? So that's another way of specifying that. So you imagine if you're a traffic engineer and somebody says, well, what are the behaviors that a traffic light should satisfy? You might write these down. And then some other engineer might come say, oh, I've designed this finite state machine that implements these. And you can go check, right? It's a simple one. You can just look and see, yep, all of these are satisfied. There's no way to go through this finite state machine and violate any of these properties. So that's the mathematical language that we can use. And that property of checking, one way to do that is something called model checking. I basically give you a system description, right, as a finite state machine about what's possible. And there might be multiple things that are possible. I don't know whether you're going to turn left or turn right, but whichever one that you do, I want some properties to be satisfied. So it can be non-deterministic, that I don't know exactly what will happen, but I know the set of possible things that could happen. I have some set of properties here written in this linear temporal logic. And then there are programs that essentially take that system description, take the property, and they basically negate the property, and then they try and find a counterexample. Right? They say, can I find an example where the opposite of the property is true? Right? That would be a counterexample. And they're basically written in such a way, they do some internal stuff that we don't need to talk about. And they'll either say, for all possible executions of this finite state machine, this property or set of properties is always satisfied. So they'll say yes at the end. Or nicely, they'll say no, and here's a specific counterexample. And that's, of course, useful for engineers, right? Because engineers always believe their designs are right. Right? And so then they come in and they say, yeah, you're right. I hadn't thought about that, right? And so they do that. And these systems are getting, quite advanced. They work for pretty big systems, so they can now check things with up to 1 billion internal states. 1 billion's a lot, but not, you can get there quickly, right? In these discrete state systems, right? Because you think about how many variables are they, and if they each have, 2 possible states, you get 2 to how many variables, right? So you can get up to 1 billion pretty quickly, but they're pretty good. They can get up to, easily 10 to the 9, sometimes 10 to the 11 states. And I think, just from a controls point of view, this is something we want to exploit, right? These tools exist, they're really good. Spin, new SMV, Prism, I mean, there are lots of them that are out there, right? Okay, and so one way to think about this is that, I've got this kind of, system over here. Here's just a different view of that. I've got a system model. I've got some assumptions about the environment, et cetera, that are also written as these sorts of properties. And I have some requirements that are my formal specification. Some of the assumptions I put into the formal specification, some of them I put into my system and environment model. But in the end, I get, here's the set of things the system can possibly do. And here's the set of behaviors that I want to check. And in model checking, we basically say, given a controller, right, that's supposed to be implemented on this system and do the right thing, given these formal specifications, tell me, right, that it's either satisfied and it will work for all possible executions, no matter what combination of things happen, it'll always satisfy these properties, or it's violated and give me a counter. And so, that is existing technology. It's getting applied more and more. Amazon uses this to check to make sure their scheduler has the right properties for scheduling time on processors, as an example. But the other thing you can do is synthesis, right? We can turn it around like we did in controls, like in H-infinity, right? Say, look, why don't I give you the system spec, the system description and the spec, and then synthesize the controller, right? So I will tell you sort of how to do this, and then I know that this controller satisfies the specs by construction. So correct by construction is kind of the term used. And when I was here last time, that was what we were working on, was correct by construction. Or it will tell you no such controller exists. It's actually not possible with this system to satisfy that spec. Ever, right? Just like in H-infinity, say, I'm sorry, right? Here's a disturbance for which you cannot possibly sort of do something. So these tools were in progress at the time. I think are still in progress. When I was, here last time, I said this is the way we should do everything. Right? This is going to sort of solve the problem of designing these discrete vector controllers. I'd say these are not getting enough. People are not using these tools, and part of the problem is that people don't trust, right, the automation, right? Yeah, but I can't understand, right, the code that comes out of this thing. It's this complicated finite state machine. You tell me it's correct, but I didn't believe this was the right model anyway, right? So, to some extent, I designed it for something that was an approximation of the world, right? Or, right, I'm not sure these were the right specs. They were the one I wrote down, right? So we've had a really hard time getting anybody to use these. And so, one way you can take this talk is we gave up. right? And I said, okay, fine, all right, let's do something different. Yeah.
Is there a reason why you don't say certificate on the right side?
No, essentially the controller that satisfies the spec, essentially is guaranteed to satisfy the spec. So you can think of it as coming with a certificate that satisfies the spec if you want to think of it. But it's not a certificate in the sense of these model checkers kind of in a very efficient way go through every possible execution, right? So it's not like I give you a Lyapunov function that I can then go check that Lyapunov function is a Lyapunov function, right? A certificate of that sort. It's more.
Would the certificate of the second sort be more convincing, you think?
No, yeah, I think it would be, right? If you had the structure to do it, right? So you could say, hey, could I give you a control barrier function to prove the properties, right? And people like Aaron Ames are working on things. Yeah, sure. All right, so one other little piece, just again, the background piece is, we do, of course, have dynamical systems, right? And they need to link to these finite state machines. You're driving a car, left lane and right lane might be something we think about abstractly as a discrete state. Am I in the left lane or the right lane? But the reality is there's a dynamical system underneath that I have some position, right? I have to decide, I've changed lanes. What does that mean? That's a continuous thing. So there is a connection between these layers. So we have ways of doing that. And so I won't go through the detail, but just to say, if you have some state space and you have some broad level regions that have meaning to you, this is in the lane, this is in front of the stop sign, this is in a parking lot, whatever these happen to be, right? Then you can say, well, now I need to figure out a transition system. And it's not the case that I can just say, well, you can go from here to here or here to here, because I may not be able to go from every point in here to here, right? Depending on what the dynamics are. Right? And so there are techniques essentially where you say, well, let's break this up into smaller pieces. This all happens automatically. And then from those smaller pieces, let's figure out what is the transition diagram that happens here, right? In these, refined sets. And they're not necessarily, you can think of it like a Markov decision process. I might tell you I want to go forward, and you might end up here or you might end up here, and I might not be able to tell you which one, right? Because there's uncertainty and other things. But we can keep track of that. We can say, look, you command this motion, and just like in a Markov decision process, either with or without probability, you might go, here or here. So we have ways of doing that, and we can essentially take these problems of looking for regions where we can move from one region to another and do a discrete abstraction of that. These turn out to be solving sort of polynomial problems, a lot like you would see within, let's say, the model, the multi-parametric toolbox. It's the same set of polynomial problems that you need to solve. So a piecewise linear system, I can construct these things with disturbances on model dynamics, all of that sort of possible. And essentially, I can get these sort of discrete abstractions in a transition matrix. So one thing to just, kind of take away from this is that if I'm thinking about a continuous controller, I can create a discrete abstraction, and these are equivalent to one another in the sense that any trajectory in the continuous space corresponds to a set of transitions in the discrete space, and any problems in the discrete space can correspond to a trajectory down here. So particularly if I have a controller up here that says go here, then go here, then go here, I'll know that it's possible to do that. And this is important, right? Because I might say, oh, you're at the intersection, just hop to the other side, right? And then I don't have to worry about it, right? But that's not possible. And these techniques will tell you, well, there is no transition that hops to the other side. You have to go through the middle of the intersection. Okay, so, I'm talking about everything discrete, and I think I just want to get across the point that, yes, there's continuous dynamics, and yes, we know how to map those discretes. All right, so the one, and again, this is stuff, that we still want to use. There's a technique that I want to make sure people understand because it's sort of the most important piece of technology that we use, which is this idea of synthesis. And I already said synthesis is something that we're not, I think, seeing people adopt, but synthesis of tests is something that we can do. So I have a process, I have an environmental description, and I'd like to design a controller. The process is something that's discrete state in this representation. The controller is something that sees what the environment is and sees what my current system state is and has to tell me what to do next. The environment may also be part of my input because if somebody's in front of me or whatever, they control whether they're in front of me, right? I can then decide to change, right? We'll assume that I can measure what the environment is doing, so I see what everybody is doing around me. That's an assumption, but if you're iterating quickly enough, it's probably reasonable, right? I may not know what you're going to do next, but if I wait a couple of milliseconds, I'll see what you're actually doing. And if I'm doing it quickly enough, effectively, I know what you're doing. And so the idea in synthesis then is to say, given this description of the system and environment, synthesize a controller that satisfies some set of specifications. And for this, generally speaking, that problem is doubly exponentially hard in the size of the system specification. So if I have 5 system specifications, it takes me 2 to the 5th, 32 time units to solve it. If I have twice that number, it takes me sorry, if I have 2 specifications, it takes me 2 to the 2 to the 2, 2 to the 4th, not too bad, right? If I have 10, it takes me 2 to the 2 to the 10th. That's 2 to the 1000th. We're done. Age of the universe, right? So it's horribly complex, which is why nobody uses this. But it turns out that there's a simplification, in particular, if you kind of take the assumption that I can kind of unwrap this. The environment makes a decision. I see what that decision is. The controller then knows the decision, knows my system, decides what to do, implements that, and then the next state happens. And again, if it's fast enough, you can kind of say that's a reasonable approximation. Then you can kind of unwrap this process, and you can show that for a certain class of specifications, and these are these GR1 specifications, right? This problem goes from being doubly exponential in the size of the system spec to being cubic in the number of states required to represent the problem. That's like telling you this is a convex program. Actually, it's like telling you it's a linear program, the amount, right? This is suddenly tractable, right? Cubic complexity, no big deal. So now there's a hidden assumption in all of this, which it turns out here I said system specification, here I said number of states. There can be an exponential factor between the system specification and the number of states required to represent that system specification, but typically not. And typically they're simpler than that. So this makes the problem tractable. This is pretty new, right? Now 15 years old, 20 years, 15, 16 years old. At the time we started, right, it was a pretty new result, right? So it's like somebody coming up with a new algorithm that, suddenly things are tractable. And it has this assumed guarantee spec, right? So under some assumptions on the environment, I want to give some guarantees. Now I want to show you just a simple example that's going to kind of capture the stuff that I care about of this. And this is this runner blocker system that was due to Punwali. And the idea is the following. Here's a discrete game, if you want. I'm this system. I start at some location. I'm the runner. My job is to get to the goal. My actions that I'm allowed to do is I can go up or I can go down. There's a blocker, the B. The blocker has 3 positions that it can be in, discrete states. It can be up, it can be in the middle, or it can be down. And I want to design a strategy such that I get to the goal and that the blocker is never in the same cell as I am. It's probably obvious to all of us, right, what we have to do. If the blocker stays in the middle, I'm screwed, right? Because if I move up, the blocker moves up, we're in the same spot. Right? If I move down, the blocker moves down, we're in the same spot. But if I assume that the blocker will not stay in the same position forever, always eventually the blocker will move. That's a linear temporal logic property. Always eventually the intersection will become clear. Always eventually somebody will let me go through, or I'll find a gap in the traffic, right? Those sorts of things. Then it's obvious what you do, right? You wait until the blocker goes down. It's sort of 1 move per turn in this way we've done this. You go up, right? The blocker may move up to the middle. That's fine. You go here, you win. So that's the strategy. So you could turn that into a controller, right? If blockers down, if blockers in the middle, stay. If blockers down, go up. If blockers up, go down. Right? Once I'm in this position, always go to the goal. Easy. All right. So how might we synthesize that, right? Suppose that we wanted to do that. So what you can do is you articulate all the possible system states. So here I just put the runner and blocker in every possible position they can be in, right? And then there's a transition system between all of those. It has 2 different types of transition. The red transition are the transitions of the blocker. The blocker can move up or the blocker can move down. The blue transitions are the transitions of the system, right? Once the system is here, I can move up, which I probably wouldn't do, but I could. Right? I can move down. Right? Same thing on the other side. And then I can keep going through. And in the end, there's this one state where the blocker is wherever it is, and I'm at the goal. We can then label these states, right? So this bottom one is a winning state. These are losing states. This is the initial state. The goal is to synthesize a strategy that takes me from an initial state to a winning state without going through any losing states. So how might we do that? Well, one way you do that, you say, well, let's start and assume I was in the winning state. And then let's ask the question, from what set of states can I satisfy the property that if the blocker takes some move, I can take some counter move that gets me to that final winning state? Because then I know I can get to that set of states too. And so if you look at it in the context of this example, it turns out that's this set of states. So if I start here or here, it's kind of a dumb one, right? The blocker is up here. I'm always going to do exactly the same thing, which is to move, but nonetheless, I can always find a move. And then you can say, good, that's a new set of winning states, right? Because I can win from those states as well. So iterate. From what set of states, if the blocker takes a move, does there exist a move such that I get into my new winning state? And I expand this. And now, right, I expand it. And in this particular case, I get to the initial state. And now I can stop, right? Because once I, this is just an iteration, right? I just keep expanding the states. And once either the iteration stops, I'm getting no new states. And when that happens, either the initial state is in that set or not. If it's not possible. If it is possible. And how do I figure out how to do it? Well, I am in some state. What I know is that whatever action, right, the blocker takes, there exists some action that I can take that gets me back into the set. There might be more than one. Here, there's only one. But this is a strategy. If I'm in this state, do this thing, right? If I'm in this state, do this thing. Don't do the other thing. Right? And so that's a strategy. That's a controller. Right? And so we can synthesize these strategies to do that and essentially get a controller out. Now, this is a trivial example, but we can extend this to much more complicated examples. So that's the idea of synthesis. And the thing to take away is we can synthesize, right, given a system description and specification, a controller that satisfies it. All right, so last 10 minutes or so, let me come back and actually talk about the problem that we're working on. So now I've reviewed all of the stuff you need to know. Right, so we'll really quickly go through this last bit. All right, so here's the problem that we were, starting to look at. It's funded by the Air Force. So, this is an Air Force slide, right? So I got to tell them why it's relevant. So Air Force gets some new airplane, an F-35, for example, whatever it happens to be. Terrible airplane for lots of reasons. Anyway, F-35. Lockheed Martin delivers the F-35, and it's got a book of specifications this big, and they say, we satisfy the specs. You're the Air Force. You're about to put people in harm's way using this aircraft. You would like to make sure it satisfies the specification. What do? What test do you run? Now, there's tons of, they've done Monte Carlo simulations, they've done all the developmental tests, et cetera. But your job as the government is to say, we're going to put people in these planes. We want to make sure they're safe. You're the Department of Transportation. Waymo comes and says this thing's safe. Your job is to say, on behalf of the American public or whatever country you're in, we certify that this is safe. One of the things you're going to do is you're going to do tons of simulations. You're going to look over the code. You're going to do all the things you would normally do, but you're probably going to test. All right. What you're not going to do is do a lot of testing. So people have done calculations about how many miles of testing would you need to do, right, in order to collect enough data to have statistical confidence that you had no more than 7 deaths every billion miles. The answer to that question is you need to do 35 billion miles of driving. Right? So you come out with a new software release, go test it for 35 billion miles. Right? You say, wow, that's no problem. I've got 1,000 test cars. Great, you just need 35 million miles per test car. Right? Great, I can drive 1 million miles a year, right, in all of those cars, which you probably can't. 35 years from now, I will be able to tell you, and by the way, I just did a new build a week later, right? So how the hell, right? So, you're not going to test your way out of this exhaustively, right, statistically. But you can say, what test should I run? And I'd like to run tests that at least give me confidence. I'd like to run hard tests, right? I don't want to go down at 2 a.m. when nobody's around, right? When there wasn't a party that night or something. There's nobody on the streets. Right. And so, of course I can drive. Right. By the way, in San Francisco, self-driving cars are allowed to drive without drivers in them between 12 p.m. and 5 a.m. Right. They can have a remote driver, but they're not allowed. You can do it without a driver. Why 12 p.m. to 5? Because it's easy. Right. There's not very many people out there. You can just stop. Right. You're not worried about people running into you. Right. But if you're doing a test, you don't want to say, well, that's my test conditions, because you have no confidence whatsoever. So I think one of the questions is, right, how do we do that? And it's really hard for autonomous systems because there's a lot of things going on. This is just a video from the Driver Grand Challenge. Now, many years ago, you come up to an intersection, right? There are cars there. You're trying to verify that nothing will ever go wrong. Here's a test that was run, right? And so, here we waited until other cars went. It's now our turn to go. Right? We sort of drive down the road. There's a bunch of controllers going on and other things, right? Some little anomalies that happened. This is a long time ago. We come up to this next intersection. You'll see there's a car in front of us, right? We stop at the appropriate distance from the car. When this car goes, then we can say, okay, good, there's no car in front of me, so I can come up, right, to the intersection. But this car was at the intersection before I was, so I need to wait until it goes, now I can drive. So that was a test they designed. But how, is that a good test? Is it hard? Do you have confidence now that I can drive in the city of San Francisco based on that test? I don't know. All right, so the other problem, I think for these is it's very complicated system, high dimensional, corner cases matter, as I've already mentioned. So how do people do this now? So one of the ways people do it, amazingly enough to me, with humans is the following. I don't know how it is in Sweden. In California, you go to the Department of Motor Vehicles, you sign up for a test. You sign up, you take a written test that says, when you have to stop, who has the right of way, all this stuff. If you pass the written test, you go sit with a driver, they sit in the passenger seat, or the inspector, or whatever, you sit in the driver's seat. And for a half hour, they say, well, why don't you drive down there and turn left at that intersection? Okay, why don't you go in that parking lot, parking that space? Why don't you parallel park? They do this for 30 minutes. And at the end, they say, Richard Murray, age 18, you are now allowed to drive for the rest of your life in any car that you want, any place in the world, under all conditions, right? Full stop. I certify that you are safe to be on the road. Pretty amazing, right? Yeah, I don't know, is that good or bad, right? Leads to 35,000 deaths a year in the United States, right? It's not terrible. It's not that many in the big scheme of things. COVID was a lot more. But is that what we're going to do for autonomous cars? Driver gets in, tells the car, drive up here, do this 30 minutes. Okay, you're safe to drive any place in the world, right? Forever, right? Any software build, right? We learn, we change our behavior, right? All those things. Well, I don't think so. Right? Okay, so one is, right, just do a driver's test, right? Not sure that's a good way to do it. Another is we do unit tests or regression tests and other things, but these are very structured, right? You're doing it in simulation, you're testing against a lot of things. We do falsification, and software you do falsification. Falsification is a little different. You're trying to find bugs, right? Here, you're trying to give the system should actually do the right thing. You're not looking for failures; those have already gotten weeded out. Right? What you're trying to do is give yourself confidence that these systems will do what you want them to do, right? Through some set of tests. So this tends to be more bug-oriented. Monte Carlo simulations, but again, you're simulating on a model. Is that really the real world? You're doing, how many of these do you need to do, right? It's not clear, right, that Monte Carlo simulation is enough. And then of course, now operational test is the final set of things that you do. But again, you can't run, right, 35 billion miles. You can't test the F-35 in every possible condition, right? So what do you do? All right, so we're kind of doing synthesis, but now synthesis of test suites. So it's still the same synthesis problem, right? But what am I synthesizing for? Not the controller, but the environment, right? I want to synthesize what the environment should do, right? So that, right, the specifications are satisfied, but it's hard. But I'm just flipping the problem around. That box that said, environment also was a little control loop, right? So why not synthesize for that? And so the way to think about this is that, you still want the dynamics, the uncertainty, and the reactivity, right? You want the environment. If I turn left, the environment might do something different than I turn right. So I have to think about, what's the action? What am I trying to do? I'm trying to make it hard. So imagine this winning set picture. I showed you, right, a version of this in Simply Think. What are you trying to do, right? You're the environment now. You know that whatever action you take, right, the system's going to eventually get you here. It was synthesis, let's say, that's what they're asserting. So one thing you might want to do is you say, look, I'm in this state here, and I can take this action, and the system's going to take that action. I want to take an action as the environment that forces the system to make a hard choice. So I don't want to, for example, take an action in the environment in which any next decision by the system automatically brings them into the winning set. That's just not interesting. What I might want to do is do one that has high energy cost or requires them. There's only one right. There's 100 things you could do. Only one of them is right. That's a little bit harder. And that's a question we can solve, right? Because that's just a synthesis problem. And I said we extract the strategy by going backwards. Normally, given that we're out here, the environment takes some action. We take any action that brings us back in the stage set, and then you try and take a good action, minimum energy, other things. Now I just flip around what I'm doing, right? Environment needs to take an action that makes it hard for the system in the next state. But that's a problem we can solve. And synthesis, right, is a way to do that. And by the way, it's much better than what's being done now in a certain sense, which is all that's being done now is a human test engineer sits down and says, what would be a hard test, right? I'm going to do the DARPA Grand Challenge thing. I'm going to put an intersection with the car in front of it. Maybe it's hard, maybe it's not. Okay, so that's kind of what we're doing. So you might have desired properties for these test sequences. Maybe you want to cover all of the system states, the environment states, all the behaviors. You'd like to limit, again, the number of satisfying actions might be one of the ways you optimize. And so, for example, you can think about, I've got a system. I start at some position. The specification here is a grid world. So this blue dot can move any place it wants to move. It wants to get to the goal when it's like a parking lot or Uber, right? Somebody calls me, I've got to get up here. And then I want to go back home, right? If somebody calls me again, I've got to get up here. I want to get home. If I start running out of fuel, I need to stop by a refueling station on the way. And then you can have an environment. This is a moving vehicle. This moving vehicle will, like the runner blocker, just move on this set of tracks. And its job is not to collide with the car. We will assume, right, that it just collided with the car. But I want to make it hard for you. I want to make you try and run out of fuel, right? Or I want to make it so that, there's only one way to go and still make it to the goal, right? And so we can formulate that in this way. And so we've done that. We have software that does that. Just show you a movie. It's not very interesting. We're at home. We go up. We refuel. This guy's moving back and forth. It's looking at this is actually solving a model predictive problem. At every point in time, what's the best action I could take to make it as hard as possible, right? And that's what's causing its motions, right? And so it went down, right? You might say I want a coverage problem, so I'd like to make sure not only can you go up around this way, but you can also go around this way. So I might try and block this off from you, right, in some way to force you to go down here, right? Happen to go down there, right? So I know now that it can go up around this way and you go around this way. I might want to make sure to go behind me and in front of me, right? All of these sorts of things. And again, these are all things that you can kind of specify, right, as part of the synthesis. All right, so, we're still working on this. This is kind of where we're at, right, in terms of things that are going on. But we have ways of doing that. Can I go 5 minutes longer? Okay, so I'll do one last example just because the students just did this for the ICRA conference and they spent an enormous amount of time. So this is work of Apurva Bonifella, Josephine Graebner, and some collaborators. And the idea here is that we want to look at a specific system. Let me skip all of the stuff that we're doing underneath the hood because that's not so important here. But here's the system. So we have a robot and it wants to rescue a beaver. The beavers are the mascot of California. And so it's a search and rescue type mission. Right? So the beaver's in trouble. Oh my God, we got to rescue. There are 3 doors that we might go through to get into the hallway, like there are here, right? 3 doors out of this one. And each door has a key, and the key can either be on the ground, the key could be, sort of in a hook or something that's in the middle, or the key could be up near the top of the door. And I tell you, I designed a system that will always complete the search and rescue mission. Right? And now you've got to design a test. So you might want to do things like say, well, I want to make sure you go through any door, not just the door on the right-hand side all the time, right? Because maybe the doors are a little different. This door has maybe a different handle than that door. I'd like to make sure you can handle all of them. I'd like to make sure that this robot, which I'll show you in a second, can either walk or stand or jump or lie, right? So when it gets the key on the ground, it has to lie down to get the key. When it wants to get the key up here, it has to jump up in the air to get it. I might like to see that you can walk and lie and jump, right? So if I design a dumb test, like the doors open, you go through, you get the beaver, you come back. Do I have any confidence that you satisfy? No. But I also don't know what you're going to do. I don't know what your controller is, right? So you might come up to this door first, or this door first, or this door first, right? And I don't want something where I pre-position the keys in a way in which if you happen to walk up to this door, the key is, sort of in the position that you would see just when you walk up and you open the door and go through. Because now I don't know that you can do anything else. So we can make a reactive environment, right? We can have the key be something that I control in the environment side. And when I see which door you come up to, I know what you've done already and demonstrated already, and I can decide, do I let you have the key or not? And so you can imagine saying, okay, good. So what's the spec that I might want to do? I might want to have a test. So I have a system spec, get to the goal, eventually goal. I have a test spec. As an engineer, I said, I want to make sure you can sit and lie and stand. So my test spec is this. That's all just part of the system spec. Now synthesize an environment for this model. What can I do? The vehicle can move around to the doors. I can decide where the key are. That's all actions that we can take. I synthesize the environment actions. The system takes a system action that I don't control. I know what they might be, but I don't control. And I want to design a test that makes sure that happens. And so we can do that, right? So we basically synthesize that test. Now, the way we do it is not using GR1 and other things. We actually convert it into a network flow problem. So that was the slide I skipped. We say, look, I've got a network of possible states. I want to cut off edges in that network so there's still flow from the source to the goal, because I want to get to the goal. But also I have some intermediate states that mean I went through all of the possible things. And when you expand out this discrete event system, you keep track of, have I seen you lie down? Have I seen you stand up? Have I seen you? And there's a state there that says, you've now done all of those actions. I want to go through that state. Right? There might be a set of states that have that property. I want you to go through one of those states. So we can formulate as a network flow problem, get from here to here, but in a way that always goes through one of these states. And then the question is, what's the reactive strategy that comes? So it's a little bit of an elaboration of what we've done so far. All right, so I'm going to show you this in an experiment. So just to kind of set up the experiment. We've done this experiment. This is in Aaron Ames's lab. This is a quadruped. There's a set of lights here that you won't be able to see the colors on very well. In a slightly nicer version, you can see it better. And what happens is the colors, when you walk up to the door, one of the colors is blue, indicating that there might be a key behind that. And then if the robot lies, it basically checks to see whether the key is behind this one. If the robot just stands, it checks to see whether it's in the middle one. If the robot jumps, it can't jump this side, we'll just jump a little bit, right? Then it checks to see if it's here. And depending on what the environment's going to do, right, it will then turn the light green or leave it red. Remember, our spec is to check all of them. And we get to decide where the key actually is. So I may not, the thing comes up here and I say, well, the key could be here or here, let's say. I know that wherever it looks, I'm not going to open the door. Now here, the doors are open, right? Just for the experiment, there are doors here. There are 3 doors. There's sort of one doorway over here. It's on this part of the lab. There's 2 doors. They're double doors. They're right next to each other. There are lights next to each one of them. You'll see it walk between them. Right? And I don't know what this is going to do. I don't know which door it's going to start with. I don't know what it's going to lie, jump, or run. But I want to guarantee, right, that I check that spec. And indeed, we can do that. So here it walks up to this door, and I'll have to narrate if you won't see it. In this door, this guy is lit blue, and so it needs to stand. It stands, and we said, oh, that door's locked. You can't go through. Even though the door's open, ajar. And then it says, great, I'll pick another door. I don't know if it's going to pick left or right, because I didn't design the controller. But it picks one of them, it comes over here. And in this one, we basically told it, we know it's already stood. We've told it now it could be here or here. It happens to jump. So it jumps, so you say, nope, there's no key up there either. Why? Because it hasn't lied down yet, right? So I don't want it to be able to go through the door yet. So now it says, okay, well, there wasn't anything there. It actually did a scan also. Check this one. We said, no, there's not one there either, because I still haven't seen it lie down. If it had happened to lie down here, by the way, I might have done something different. Now it comes over to this one. If this one, right, it says, well, there might be a key down here. It lies down, right? It says, oh, yeah, there's a key here. Why? Because now I've done all three, right? And so it's okay. So now it goes out, it sees the beaver, right? It rescues the beaver, right? And it comes back through. The beaver rescue is a little bit magical. It will suddenly just pop onto the top. And it goes back through. Okay, so the point of this is, this was synthesized. I synthesized this test, right? I didn't design by hand as a test engineer. I just told it, this is what I want you to do. Here's the system description, all this stuff. We covered it as a network flow problem. We solved it out. And this is something I think we can get people to adopt, right? Because right now, how are they doing it? A human's doing it with very little guarantees, et cetera. Now I'm going to synthesize a test that I guarantee you will satisfy the system spec. It's possible for you to solve it. I'm not giving you impossible things. And you're satisfying the test specification right here. Okay, so that's probably all I have time for. So I'll end here. This is the start of the slide that I gave you, sort of 4 years ago. And so now we have this kind of notion of GR1 synthesis and focusing not on synthesizing this guy, but on synthesizing this guy, actually both of these, right? This is the static environment where the doors splitter. We actually synthesize for both. So we've kind of changed around the problem that we're looking at, but there are lots of open problems, right? How do we optimize coverage of states, coverage of specifications, coverage of behaviors? How do we link the experimental testing to model-based approaches, right? We're certainly going to do both, right? So how do I know when the models are good, et cetera? We can use those models. We don't need to use where to use them. And eventually, the real big question is just, I want to make sure that in the 10 tests that you're going to run, that at the end of those 10 tests, you say, it is safe for me to put this self-driving car out on the roads of Lund and be comfortable, right? That it will be at least as good as you said it was going to be. Okay, so with that, I will stop.
The first bullet already, how we optimize the coverage. How would you approach that?
Yeah,
I think that's one of the key challenges in this.
Yeah, I agree with you. And what you're not going to get is, so if you do code coverage, for example, right, just normal code, you want 100% code coverage usually. So you write unit tests that go along with the pieces of code that aren't. Operational test and evaluation, you're never going to get 100%, right? So you might want to say, here's some critical states that I want to cover. We did that. In the example, I said, I want to cover the lie state, the stand state, the jump state, right? So one way to do it in terms of just assuring coverage is to tell me which states. Now I might say, well, by the way, I'd like to make you move around as much as possible. I'd like to see on the left-hand side of the room and the right-hand side of the room. And I can put metrics on that in those network flows, right? I can put weights, for example, right? That say something like, if I choose a flow path through that's very short, that there exists one, that's actually bad. I'd like to choose a set of reactive states that force you on a long path so that you have to cover more states. That might be a way to do it, right? So you put a metric on, right, the paths that are allowed. And again, in the way that we do this, we have a network of transitions, and I get to block certain transitions, right? The door's not open, right? I decided that, and I said, if the door had been open, you could have transitioned here. I told you it wasn't, so I blocked that one off because I wanted to force you through some different part of the graph. So that might be a way to do it.
Yeah, but that concerns only the second step, the synthesis of the validation.
Yeah.
What about the first step, coming up with a model in the first place?
Yeah,
that model is complete for the application.
Yeah, that's a great question. So as with all things, right, all models are wrong, some models are useful, right? And so we know that the model at the level of abstraction is incorrect. I didn't take into account the fact that the quadruped might slip. It might, the surface might do slip or it can't turn, right? There are all sorts of things that we know. In my model, I said, if the vehicle goes over here, right, the following thing will happen. So I think all of these are still restricted to, it's a model-based synthesis of the test, right? And so it won't have any information that your model doesn't have in terms of what's hard, what's easy. And so you could put in a more complicated model at the risk of, right, having it become more intractable. GR1 synthesis is pretty good, cubic, but if I have 1 billion states, that's still a lot, right, to sort of solve for. So one thing, and we haven't explored it yet,
So to take that into consideration, that the initial model would be insufficient or incomplete, and then take that into consideration during the validation.
I hope so. That's the second bullet. So how do we, sort of link these things, right? So one thing you can say is I tested all of these things on the models, and to the extent that my models are accurate there, I validated all these things on the model. And to the extent that I believe my models are accurate, I don't need to test those, right? Because basically coming to a stop sign, turning left, right, etc. Maybe say, the models are fine there. Don't test that. But here's spots where I don't trust the models. Right. And so test those. Yeah, I think that's what we'd like to do, right?
Okay.
How, I don't quite know. But one of the things, I hope this comes across a little bit, it is a rich space for asking these types of questions and coming up with sort of new ways of thinking about it, right? And again, we've not found a lot on synthesis of test. In the computer science world, you see a lot, but it's more on falsification and other things, synthesis of unit tests, things like that. For these kind of mixed systems, decision-making systems, less so, right? Especially within a complex environment.
Thanks for the fantastic talk. I have two questions. One is like there is another level of thing like the rationality of drivers that are actually driving behind.
Yep.
Some might be driving for cheap thrills, and some might be driving so fast to get to their destination fast. So how do you actually model? When you're driving, you have to see like how the other person is also driving. So that is one. How do you actually get that into the abstraction here?
Yeah.
The second question is, you mentioned that it's possible to specify the specification using the temporal logics here.
Yeah.
So there are like infinite number of scenarios.
Yep.
So how would you possibly enumerate all those scenarios using the temporal logic?
Yeah. Okay. So, just on the first one, there's different types of drivers and different cars and all these things. How you figure. So there are a couple of things you can say. So one is, of course, some of that I can encode, right? I can say you can drive fast between these things, you can drive slow between these things, you can signal before you go, you cannot signal before you go. And then I can simply say what's a hard test, right? And so again, I can't test everything, right? I can simulate maybe a whole bunch of things. So you might simulate things where you say, oh, sometimes people don't signal, right? And so I need to, have simulated that and make sure the car responds right. So some of that you can get, again, if you have a model for what aggressive behavior is, or safe behavior, or satisfying the rules, etc. Another piece of that is we do assume in this that the environment will not take actions that lead to inevitable failure. Right? Now you can say, well, that's not fair because people do things that you just can't do anything. And the answer is, yeah, but you're going to crash when that happens, right? If somebody cuts in front of you without enough speed to stop, you're going to crash. And I can't do anything about that, right? Self-driving cars are not going to have zero accidents. They're still going to have accidents because people are going to cut in front of them and accidents are. And that's not useful probably to test, right? I might want to do the one where you could barely stop just in time, right? Because then I know that, by the way, if somebody cuts in front, you couldn't stop, you probably stopped as fast as you could, right? And so, that's maybe the best you could do. So I think that we assume in this, and we can argue about whether it's good or bad, that the environment will not take an action that makes it impossible to satisfy the spec. Even though we know in the real world it will. And that's where you do the fault tree analysis and other things. I want to make sure that happens seldom enough. Now, just this sort of vast complexity of everything, again, I think you can come back to the non-operational test and evaluation part and just say, if I've got simulations, right, can I really simulate everything? Right? And, I think what people are doing is they're trying to say, no, I can't simulate everything, but I can try and simulate something that gives me statistics that are good. I can simulate 35 billion miles of driving. Right? I can put in artificial agents and other things, right? And I can use that to give some level of confidence. Does that cover every possible scenario? Absolutely not, right? But can I say with 99.999% certainty, you won't kill somebody, right? Maybe, right, based on my simulation. And by the way, aircraft are also not guaranteed not to crash. They do crash, right? We're simply trying to get the statistics of that low enough, right? So you want to sort of say, I'm capturing enough of the scenarios I know about that I know they're unknown scenarios, but I have high confidence that because I do so well in the known scenarios, right, that will carry over to the unknown scenarios. And if it doesn't, we'll find that out, unfortunately, the hard way. 737 MAX will crash, right? Equivalent to that, right? And then we'll go in and say, okay, we need to design a new test. It's iterative, right? The aircraft industry was very unsafe at its start, right? People were dying, government came in and said, this is not acceptable, right? So we'll see that same iteration, right? Having the self-driving cars. I think the question, as it was with the aircraft industry, will the industry survive? Right, because if the industry dies because people can't, the liability is too high, et cetera, then we won't have self-driving. which,
So we are running out of time, but
yeah.
I take the chance to ask one more
So, okay,
myself.
department chair prerogative or something.
When you speak about model-based, the question, there's a difference between the tester building the model or the provider of the equipment to build the model. You could ask them, you have to give me a model which is satisfy certain specifications, and then I can start working with the model, and then and then they could fail already at the model testing phase.
Right. Yeah, I think the way that we would like to do it, if we can, and we haven't formalized this completely yet, we'd like to say, one model that I think is fair to give is the model of the physics of the system. Can I turn left? Can I turn right? You know, what is allowable right under the physics system? I can't hop across the street, right? Things like that. What I don't think we want to do is to have a model of the controller, right? Because that's what I'm trying to test, right? If I've got a model of the controller, I don't want to exploit structure of that because I'm not testing it. But I do have the specs that the controller is supposed to satisfy, right? So can I take a model of the physics of what's allowable and the specification of what you were trying to solve? That's what I'm trying to test after all. And say, here's a reactive environment, right? That will, right? Fits within the set of things that are allowable. You should be able to turn left. You should be able to go straight. You should be able to do these things because the physics of a car allow you to do that. And you should have done so in a way in which you obeyed the traffic lights and stayed in the right lane and all these things. And so I'm going to structure a test to do that. So I think we got to be careful because, yeah, you don't want the testers are using or using models the developers did. By the way, in the kind of formal way that this is done within, say, the military, on purpose, operational test and evaluation is completely separated. The companies actually aren't allowed to do this, right? A different organization has to come in. So they're not biased by, here's how we design the system to operate. So we design the test to test the thing that we design, right? That's not useful. So they are intended to be independent, but it's a great point. You have to figure out what's the allowable level of knowledge. It can't be nothing, right? But it can't be everything, or shouldn't be everything.
Okay, thank you very
Great.
much.
Thanks very much.
Okay, if there is someone who is not on the schedule remission this afternoon, I think there is still maybe not a stop.